Hello, we are Team 4, and our project was over crowd-aware robot navigation with attention-based deep reinforcement learning. So this will be the flow of our presentation today. First, I'll go over the paper. The paper we chose is Crowd-Robot Interaction, Crowd-Aware Robot Navigation with Attention-Based Deep Reinforcement Learning. Prior works tended to frame the problem as one-way human-robot interaction problem. The goal of this work was to explore this problem by looking at the crowd as a whole and exploring the concept of crowd-robot interaction more deeply. Their claimed contributions of the paper were a self-attention mechanism that learns the collective importance of neighboring humans with respect to their future states, being able to jointly model human-robot and human-human interactions in the RL framework, and a model that can anticipate crowd dynamics and navigate in time efficient paths outperforming state-of-the-art methods. So the network consisted of 3 modules: the interaction module, polling module, and planning module. First is the interaction module. This module explicitly models the human-robot interaction while using local maps as a coarse grain representation for the human-human interactions. Next is the polling model. Interactions between the robot and each human are extracted from the interaction module and subsequently aggregated in the polling module. The purpose of this module is to learn the collective importance of neighboring humans with respect to their future states. Finally is the planning module. This estimates the value of the joint states of the robot and humans for navigations in crowds. Based on the compact representation of the crowd, it estimates the state value for cooperative planning. So the simulations conducted were used with circle crossings where the human agents were trained with Orca. All humans were randomly placed on a circle of a radius of 4 meters and their goal positioned were on the opposite side of the circle. To evaluate their model SARL and OM SARL, they implemented 3 state-of-the-art methods to use as a baseline. Next, I'll go over the related works. So the first related work was published in ICRA 2021. The main idea of their paper was to explore more challenging robot crowd navigation with a novel DSRNN network that incorporated spatial-temporal reasoning. To create more challenging environments, they created group scenarios. In the picture on the right, you can see examples of this type of scenario. The yellow denotes the robot, static humans are grouped into circles, and the rest of the agents are moving. They did this to simulate the scene of a dense crowd with both static and dynamic obstacles. All the simulations were done with circle crossings. Our next related work was also published in ICRA 2021. Its focus was on crowd navigation in complex environments with non-holonomic robots. This paper proposed a reward function they called RSORL, which is an augmented version of the reward function proposed in our chosen paper. Additionally, they wanted to create complex environments that would make navigation more challenging, and each simulation included 15 agents, 5 used as static humans, and the rest dynamic humans, which could be seen on the right. Additionally, the robot is unicycle, meaning that its movement is very restricted. So you can see examples of their environment. Environment A has 5 separated obstacles. Environment B has 2 barriers of 2 and 3 obstacles, and environment C has 1 concave barrier with 5 obstacles. Next, I'll go over our reproduction and implementation process. So the paper's source code is available in GitHub, and we refer to that for our implementation. We use these specifications listed to implement the code. We use the source code from the GitHub repo as a baseline and train the model with circular crossing cases. It took over 9 hours to train 10,000 episodes with our CPU, and the visualization of an initial test case is shown on the right. We compared our replica model with the paper's one, and due to time, we only tested with Orca and SARL. We found that our results are comparable to what the authors published in their papers. And in the SARL case, our model was actually slightly faster and it had a higher reward than the paper. Next, I'll talk about our contributions. While reading the paper, we felt that the simulations were implemented with 2 idealistic conditions, meaning such as the robot only avoided moving humans, they do not consider the presence of constraints in the layout, and they only tested on spacious open environments. And so our improvement plan had 2 main components. First, we wanted to add more real-world scenarios. For us, that included using a combination of both static and dynamic objects, increasing crowd density, but also different environmental spaces. Next, we wanted to introduce more natural human movement. We felt the circle crossing simulation didn't really make any sense for the purpose of this study. Like you can see in the GIF, circle crossings forces all the agents to move and cross in the middle. But crowds in real life move in a much different way, and so we modified the human pathing in a way we thought more accurately represented a crowd. Next, I will talk about our simulations. So we created 3 simulation types: an open map with static objects, an H-shaped map, and an S-shaped map. Each simulation is created with the intention to replicate real-world situations and to cause the robot to have more interaction with the humans. And so first is the open map, and you can see we wanted to replicate this kind of scenario. So static objects are scattered around with an open map. Next, we have the H-shaped map. So we wanted to recreate a crosswalk type of scenario. People can walk freely on either side, and there's a narrow dedicated crossing section. Like so, and finally, we created hallways. We recreated a scenario with hallways. Hallways are more narrow, and so there's more prone to collision. So we thought this would be a good testing case.
I'm Chejino, and I will present about our methodology. And in obstacle, we implemented obstacles instead of the static agent, unlike before, because the static agent before with Orca does not act like an obstacle because the other agents are closer. The static agent was moving, so we need a real obstacles which does not move at all. So it could add more diversity to the simulation as well. In fact, the RPO simulator we used to support obstacles, so we used add obstacle method for the human agents. We fixed the shape of the obstacles as a straight rectangle for sake of simplicity, and we give 4 parameters, which is position and size of the rectangle. However, we need to handle the collision cases for the robot, because robot cannot recognize the obstacle yet, because the simulation is based on the human agents. So we determine the collision case by calculating the minimum distances and regard as collision if the minimum distance is less than radius, like the figure. I compare all possible candidate distances, like the distance between the robot's center with 4 vertices and with 4 edges, and calculate the minimum distance by comparing the 8 distances. Also, I implemented obstacle map, which is a JSON file that indicate the maps, and I use JSON file to handle configuration of obstacles and maps. Then that is include obstacles position and size, and possible space of the start and end position of humans, and start and end position of robot. And we added 3 maps like we mentioned before: H shape, which indicate crosswalk, and S shape, which represent the hallway, and the open map. And in training, we split the training for 3 maps uniformly, and each maps will take turns sequentially for training, and this is for preventing catastrophic forgetting issue. And for each map, we used obstacles to limit movements. In H shape, we add 2 scarce obstacles at top and bottom, and in S shape, add 2 horizontal rectangles in 1/3 and 2/3 of height. And in open map, we randomly add up to 2 small squares. And due to the long training time, training was not complete. And in evaluation, our simulation setup was like this. And our evaluation is each map type was trained with different number of episodes because of the long computational time and mistake. And we trained 10,000 for H-shaped and 2,000 for each other 2 maps. And we tested 200 episodes for each map, totally 600. And our results. This is our samples from test case. If you're interested, please see this. And we were not able to get success ratio on the test because training time was almost twice longer than we expected, and test also takes long time, over 1 hour. However, we were able to get 89% success ratio on H-shaped as the result of validation on 10,000th episode of H-shape, like here. And discussion. Our model were able to achieve higher performance in natural cases, like in H-shape or S-shape or OpenMap. The paper's SARL has only 41% success ratio on H-shaped map, but our model got 89% success ratio in validation test. In this project, we were focused on the real-world applications for the robot, and we considered considering more practical cases would be more useful to the real-world application. And our limitation. Our project were too CPU-intensive training. So original implementation used CPU-intensive simulation. So the training time takes 9 hours. And we cannot use the GPU accelerated version. And with our modification, the training time has extremely increased, and like 18 hours for 10,000 episodes with 5 human agents and 3 maps. Also, due to the long training time, we were failed to train as we planned. But we could train again to get the better results further. Also, we used the ORCA for human agents, but they did not applicable for us for this project. ORCA usually stuck in H-shape and S-shape cases like this here. The robot doesn't move at all. And training, because of this, training would not perfectly be done as we want. So if we succeed to train the SARL, we can give the SARL policy to human agent as well. Thank you for listening. And this is the end of our presentation.